All righty. Welcome, everyone, and thank you for being here for Passive House Accelerator Live, where we explore how to slash the greenhouse gas emissions from our buildings and make them more resilient to the impacts of climate change. I'm Zach Semke, director of the Accelerator, and we are excited about today's presentation by Gary Klein about maximizing efficiency in hot water systems. Our co-hosts of today's construction tech episode are Kevin Brennan, Ilka Cassidy, Shannon Pendleton, and Sean St. Amour.
Hey guys, I'm Kevin Brennan. Welcome to Passive House Live Construction Tech Edition. It's a great privilege to have Gary Klein on. My first meeting of Gary Klein was at summer camp, at Building Science summer camp. I wandered my way upstairs to a meeting place and heard Gary talk very passionately about hot water and distribution, and my mind was blown. As an energy efficiency nerd, the last thing I was really focusing on in my energy models was hot water. But now, as I advance my career through efficiency, I'm working in Passive House. The frontier of efficiency is hot water. There's a lot of improvements that could be made, and some things as simple as piping design. And I always learn when Gary's on, so keep your questions ready. And just to set the tone, I do believe Gary would prefer that there are two types of questions. Some questions are clarifying questions that we're talking about, which you can butt in the chat and just say, hey, can you clarify this? And then the other questions are more specific, where we expand on topics and divulge in new areas. I may have said that quite a little wrong. Correct me, clarify if needed, but I'll pass it off to the next co-host, which I believe is Sean St. Amour.
It is. Thanks, Kevin. Great stuff. And so if you haven't done your homework, if you haven't watched Gary's two earlier presentations, the next comment might sound awkward, but this is what happens. Every time I take a shower, Gary's joining me, because that time to tap ratio of how it works out, where I'm standing in the cold waiting 44 seconds because Gary told me that my rental didn't have the proper plumbing and recirc lines. It happens. So if you haven't watched those two episodes, go back afterwards, check them out. And yes, Kevin, one thing that we want to look at is, what would you like Gary to answer today? Fill up the chat. Want to make sure that any questions you have regarding that whole thing is taken care of. And other than that, sit back and enjoy Gary. Over to Ilka.
Hey, everyone. I'm really excited about this presentation today as well. I think my first time hearing about Gary Klein was when I was struggling with my hot water distribution on my first passive house, probably around 10 years ago or so. So I heard that Gary can answer any questions, and I believe I just called you up and asked you. So while you're not in my shower all the time, you're definitely with me every time when I look at my hot water distribution when I was trying to figure that out on my passive houses. So yeah, next to Shannon.
Amazing, Ilka, thank you. And I am in that same camp. I look to Gary when I lay my plumbing out in my designs. And after today, you will too. I definitely did my homework. I have some pictures of plumbing manifolds and wimpy shower heads to look at later in the presentation. But I am really excited to be here with Gary today and have you all join us. I hope you've had a great start to your new year. And we're grateful that you're here. So Gary Klein is president of Gary Klein and Associates, Inc. He's been intimately involved in energy efficiency and renewable energy since 1974. Since the early 90s, he's led the effort to incorporate hot water as a system into the core principles of building science. After serving 19 years with the California Energy Commission, he's provided consulting on sustainability since 2008, with an emphasis on water, energy, carbon health connection. So the benefits of right-sizing premise plumbing and water heating systems are currently at the top of his list. He received a BA from Cornell in 1975 with an independent major in technology and society. That is not a surprise, given what his presentation titles are today. You'll see what I mean. So he emphasizes energy conservation and renewable energy. The International Association of Plumber and Mechanical Officials, the IAPMO, has recognized his efforts in 2014, and they presented their Green Professional of the Year award to him. And in 2015, the Department of Energy awarded Gary the Jeffrey A. Johnson Award for excellence in the advancement of building energy codes. So as you can see, for the last 30 years, Gary has not been busy. Gary, thank you for joining us today. Please take it away. And while you're watching Gary's presentation, ask yourself, what do you want Gary to answer today? What is your question for Gary? And please put that in the chat. Thank you.
Thank you all very much for inviting me to speak on hot water today. I want to do a couple of fun things today, as well as teach some science and engineering. So with that, let's just get started. I'm going to show you, I found some stuff on my computer that's over 20 years old, where I've been teaching some of the stuff that you've heard me teach more recently for many, many years. It's always entertaining to go back and see what I said way back when I got started. So, some questions. Do you know anyone who waits a long time to get hot water somewhere in their house? Raise your hands. You can all do that electronically too. You probably know somebody. If it's not you, it's a friend. Any customers who complain about waiting for hot water? Any communities that have a water efficiency or water supply guarantee ordinance? You can't build unless you can guarantee your supply of water. How about communities have building or appliance energy standards or incentive programs? That's what we work in, right? That's our space. Any buildings inspectors that would like to be more efficient and effective at inspecting hot water systems? Any builders like to improve their process for plumbing bids? Any plumbers would like to provide better value for their customers? Anyone who would like to learn how to get hot water to every fixture, wasting no more than 1 cup after you wait? 2 hands. I see 2 hands here. You can raise more than 1. So if you look carefully, I presented this to the Affordable Comfort Institute annual conference in May of 2006. That's a few years ago, like almost 20 of them. I've got computer stuff on my computer that goes back to 30 years when I first got started. And I guess what I should do is to share why I got started. But while we do that, you can look at this energy pie. I was hired to work for the state of California in 1990 to do an energy efficiency report. Actually, it was called the Energy Conservation Report. It was one of the 4 or 5 feeder documents to the Integrated Energy Policy Report, and I was leading one of the segments. It was called the Energy Conservation Report. When I was hired, it was published as the Energy Efficiency Report. That has to do with public policy changing the words to use. Didn't change the fundamentals. So I had the unique opportunity of adding up all the energy beans in the state of California. And we created a set of tables that you can add, subtract, multiply, and divide for both supply and demand, and they're internally consistent. So I know the units of energy use in California pretty well. And I certainly knew them in 1990, which is when we did the report. If you look carefully, heating and cooling is the blue, and water heating is the orange, bright red, whatever you want to call that color. And there's lots of little things you can't even see, like vampires. It's in here somewhere. All the stuff we talk about, some of it didn't exist much back in the 1990 energy patterns. Let's see, who had a computer on their desk in 1990? Not many of us. It was new, right? Wall warts were new. Set-top boxes were new. All that stuff was sort of new. All right. So I was working for the Energy Commission looking at this energy pie. And so I'm a pretty simple guy. I decided after the report was over, I would start working on how to improve energy use in California, residential applications. And I went in and I decided that since water heating space conditioning was number 1, water heating was number 2, I'd work on space conditioning first. Start with the big ones, work your way down the list. Sounds like a good plan, okay? So we looked forward for the 2010 and 2020, and you'll notice that we've been improving the efficiency of space conditioning systems. We're building more efficient envelopes. We have better windows. We have less air infiltration. We've got lots better and more efficient equipment. Water heating hasn't changed as a fundamental basic number, and it is now bigger than space conditioning was back then. Okay. In 1993, I got a call from somebody who asked me how long it took to get hot water at the furthest fixture from the water heater in my house. After making him wait a year for me to give him an answer, I stood there one Saturday morning with a bucket and a stopwatch, and I measured 4 gallons in 4 minutes till hot water got to the shower in my house. We lived in a 1,600 square foot US median home the year it was built in 1978. For the energy geeks, that was the first year of Title 24 California's energy standards. And my house was only missing 16-inch by 4-foot long bat in the whole house because I measured it with an infrared camera. I knew. Okay. Single pane windows and a COP for my air conditioner were about 2, but nonetheless, I had good equipment at the time. And the house wasn't bad. But I could see the pipe. I told you it took 4 gallons in 4 minutes till hot water to arrive. I had less than 2 gallons of cold water sitting in the pipe from the water heater to our shower. Why did 4 gallons or more come out before hot water got there? I couldn't explain that from first principles, which is what got me started on this quest. And I've been researching how and why hot water is inefficient and how to make it more efficient for its delivery and its production for 30-something years. So I'm always working on the biggest item, but about 2006, I decided there were lots of people working on space conditioning and no one was working on water heating. I decided someone needed to, and I looked in the mirror and said, it's up to you, dude, get started. So I've been on this quest for almost 30 years now to do this work, to try and figure out hot water as a system. Why? I knew then that it was going to become bigger than space conditioning because we were doing nothing to improve its efficiency. If you don't do work on something and you do work to improve everything else, guess what? The one you didn't work on becomes a bigger and bigger percentage of what remains. So here was my projection for where we would be for the California Energy Pie in 2020, and I wrote that projection down in 2012. I have not gone back to check. It would be fun to do it, but I haven't done that yet. It just takes a little more time. Space conditioning has gotten bigger again. Has gotten bigger again, and water heating has gotten smaller because we've done something to improve efficiency. And I'm going to contend I missed my guess. We didn't make these improvements. Water heating is still bigger than space conditioning in almost all new homes, even if you just built a minimum standard. And it's certainly true for all apartment buildings. Again, even if you build a minimum standard, and the group on this call is building way past minimum standard for construction. So envelope and space conditioning and all that stuff is much, much lower. Water heating is still a big percentage. So I used to ask these questions. What do you want from your hot water system? People would answer clean clothes, clean dishes, etc. They want enjoyment. You know, those 30-minute showers have nothing to do with getting clean. Okay? Certainly if they're a significant other. I mean, come on. We want enjoyment out of the thing too. We want the service of hot water, however that is defined. And what we expect is safety, reliability, and convenience. And people expect this stuff. They want it to be relatively easy to operate, inexpensive. They want it to be safe. They don't want harmful bacteria. But what people want most, the service of hot water with what they expect, safety, reliability, and convenience. They want that as efficiently as possible. Efficiency is not the first, second, or third thing in the list. It's the 10th on a list of 8. It's not what we look at as consumers. I've interviewed over 50,000 consumers about hot water. I've been busy in 30 years. And I'm pretty sure they're telling me what they believe because there's nobody, saying otherwise in the room. So what's my recommended design procedures? This is from 2006. You've heard me talk about it today. It hasn't fundamentally changed. First, you need to decide how much water you want to waste while you wait for hot water to arrive. That tells us the plumbing system. It's that simple. It's all about the volume. You tell me the time to tap or the water you want to waste. We work backwards to design your plumbing system. Any architects on this call? You all got to give us better floor plans. We give floor plans. We have floor plans where we put the wet rooms to the far corners of the building on all floors and the water heater somewhere else. And then we wonder why it takes forever to get hot water to the fixtures, or why it costs so much to put in a recirc loop to overcome the problem. I'm sorry, we designed the problem in. We should undesign the problem. We should fix it so we have much better plumbing and mechanical cores to make our equipment costs much, much lower. And give the give the dry rooms the views. Do you really need the second bathroom to have a view of the mountains? I live in Lotland. My view is my neighbor. The view might or might not be any good. Either way. And so why are we doing that? We're giving people a dream. Let's give people the windows with the rooms that are dry so everyone can enjoy them in the whole house. Anyway, one of my pet peeves. We want to plan to install pipe that is less than that volume between the fixtures and the loop. How much depends on restrictions in the plumbing. You have to plan to insulate the loop and the branches. You want to pick one of our structured plumbing designs. We design and build a code and then verify that as-builts perform as designed. Don't we do that for most of our envelope and most of our heating and air systems? We verify stuff. I don't think that's allowed in water heating, at least not yet in my knowledge. You've heard me talk about elbows, elbow sweeps and swoops. These were early pictures of what they would look like. Okay. 90-degree turns are clean, neat, clean, and straight. If you can get the hypotenuse, you have a shorter run of pipe and it's smoother. The really wide radius elbow, we even have wider ones than this. We call those swoops. Radius of curvature is roughly 10 times the nominal diameter of the pipe. The less tight the bend, the easier it is for the water to go around it. One of Gary's rules, if you're going to plumb with flexible tubing, there shall be no hard 90 elbows. Period. Bend the pipe. If it's PEX, it's bendable. It's easily bendable up to 3/4 inch. It's not so easily bendable after that, but it is possible. We've got folks on the call who know how to do it, will happily teach. But the fundamentals are minimize your 90-degree elbows. I'll give you one in a building that has 1,000 elbows. Give out awards if they can do it with less than one. It's possible. Just have to think harder. Plumbing up is shorter than plumbing down, except when you have to go back up and down under a slab. It takes an extra 4 feet to get up and down under the slab, more than you would have thought. Anyway, these are some simple rules of thumb to keep in mind as to why distances matter. Most American adults are approximately the height of 1 cup of water in 1/2 inch plumbing, from 5'2" to 6'7", 6'8". Okay, it's easy to plumb up within a cup. It's hard to plumb down within a cup. How many buildings are being built today where the first floor is a slab? A lot. Sometimes that's called a basement. A lot. Okay, somewhere around 80% of all homes in the United States today are being built on slab or with basements. The rest are with raised floors. Okay, the only place we get to plumb up is from the first to the second floor, the second to the third floor, when we can put the plumbing below the floor and plumb up. Island sinks are always a problem. We have to talk about those. All right, here's one of my challenges that you've heard me talk about. I started doing this more than 20 years ago. If you could do it, how would you deliver hot water to every fixture, wasting no more than 1 cup after you turn on the tap? Put your ideas in the chat. I'll wait a couple seconds and we'll see how many of you get them right. There are 5 ways, by the way. There are not 6, there are only 5.
Thanks, Gary. I think that's about halfway, just so you know.
Thank you. We're good. Anybody putting anything in the chat? Well, we'll see how they do. You watch it for me. So there's 5 possible solutions. Central core plumbing, meaning all fixtures are really close to 1 water heater. That requires a better architectural plan to do that. 1 water heater for every hot water fixture. That's the logical opposite. You didn't want to buy 1 water heater. Why would you want to buy 10 or 15? I'm confused. Okay. How about 2 to 3 water heaters per home? Maybe you can group some wet rooms together, the public rooms, the private rooms, that kind of stuff. And you have 2 or 3 water heaters. Again, you have to buy 2 water heaters. You got to think about that. And since no one likes to give us space for mechanical rooms, where are you going to make that room for? It's a real problem. We could put heat trace on all of the pipes. It's a great way to keep the pipes warm. Okay. Electricians and plumbers don't always like to work together that closely. but it's certainly possible to do it. People worry a lot about what will happen in the nth year when things start to fail and you have to replace things, since we bury pipes between floors and in walls and between floors. It's a problem to get at. If we had better access, we could be more comfortable with the decision. How about we put a circulation loop 1 cup from every fixture? That turns out to be the most buildable option to overcome distance. We have to overcome distance. It's all about the volume. Okay. So efficiency strategies for hot water systems. I used to talk about wring out the waste, improve the efficiency of hot water use, increase the efficiency of making hot water, in that order. People don't want to wait for hot water to arrive. That's an unintended waste that ends up being there because we designed a building a certain way and we plumbed it a certain way. Get rid of those wastes. Then we want things to work well, and maybe we get to use a little bit less water while we're using it or for what we're doing. I am not trying to tell people to take shorter showers. It's just a waste of time and breath. It's just not the way to go after what people's hearts and minds. Anyhow, and then we can increase the efficiency of making hot water. Mostly people come to me and tell me about their new hot water system, their new water heater, the new way to make hot water. That's the last thing in my list, not the first. Okay, now let's go forward into the future. Now here's the things I talk about. There are 4 of them. Reduce the time to tap, reduce the pressure drop, install pressure-independent faucet aerators in showers, and increase the efficiency of making hot water. We're going to cover all those briefly today. As I said a couple of minutes ago, it's all about the volume. I do my design work for most plumbing systems at 1 gallon per minute, regardless of what the actual flow rate is. Most of you are working with WaterSense. You live in California or Colorado, you're using state required rules. Doesn't have to say WaterSense. You're limited for your showers to 1.8, kitchen sinks to 1.8, private labs to 1.2. All gallons per minute. So I'm saying that pretty much all of our flow rates are trending toward or are at a gallon a minute already. If you want to ensure that building will have hot water effectively and efficiently over time, you have to future-proof the building by guessing what the flow rates will go down to. I'm pushing back on flow rates going down until we right-size the plumbing. Because if we don't fix the plumbing, we're just making a problem get worse and worse, and that's just sort of silly. We know better now. If you tell me you're using really low flow rate faucet aerators, I'm going to use the 1/4 gallon per minute design column. If you want hot water to show up in less than 10 seconds, there cannot be more than 10 ounces of water in the pipe to start with. That's it. That's the magic number. You want it to arrive quicker, less volume is what gets you there. Now, volume is a question of length and diameter. As some folks on this call know, at a gallon a minute, you could use you could use 1/4 inch tubing for a gallon per minute of flow, and you would lose less than 1 PSI per foot. If you have high starting pressures, you could afford to give away some and still have 1/4 inch tubing, which means you gain length or reduce volume, or both. You get to do this. Right sizing. One of the strategies is to right size the plumbing. In 2017, the International Association of Plumbing and Mechanical Officials, through the We Stand project, published their first document on the water demand calculator. It became part of the plumbing code, Uniform Plumbing Code, the next year in 2018, and continues to be in their operational code every year, every cycle since. What you see here is that you can reduce first costs by somewhere between $600, $1,200 per apartment in first costs by right sizing the plumbing. You get to right size the hot, the cold, the mechanical room, the service entrance, the water heater. There's lots and lots of places to save money in construction by right sizing the piping. You can do the same for single family. Single family is 1 unit, so the savings won't be quite as dramatic in most cases, but some of us work on some pretty big houses, and that's worth looking at. Okay. Measuring the pressure drop in pipe and fittings. I set up a lab in 2015 in Downey, California with SoCal Gas they built a room to teach hot water and called me and told me about it after they'd built it. So I went there and started to use it. Some of my friends came with me for this exercise, and we built that rack that you see here. And that rack now contains over 1,500 feet of pipe with and without fittings, 50 feet of pipe without and with fittings for different diameters. We then built a lab for the plumbing union on one of their training trailers. And this is the third lab that we have. It was in Arcata, California. And we basically took the idea of 50 feet and shortened the length to 16 feet with 10 elbows so that we could easily test elbows really, really quickly. And you get an answer, divide by 10. It's pretty quick to get your numbers. This is showing you what some of the setup looks like. Yes, it's in a tent. We were working on a friend's farm in Arcata, California. And so we had to be able to put everything on wheels and set up out in on the patio to get our work done. Okay. And this is what it looks like. We have discharge using some very special aerators I'll talk about later. We've tested straight pipe. We've tested bend supported elbow pipe. We've tested 90-degree bend pipe. We've tested large, long loops. We've tested coils. All of these different kinds of tests with different fittings, elbows and T's in particular, some couplings. What we've measured, we now have 70 different combinations of pipe and fittings for which we know the pressure loss at 2, 4, 6, 8, and 10 feet per second. We're not guessing anymore. We're not using rules of thumb. We know the number. It's really helpful. We've also measured the pressure drop through tub shower and shower valves. Modern shower valves are anti-scald shower valves. Does anybody remember doing the shower dance? Someone flushed the toilet, you had to get out of the way fast before you burned? Okay, me too. That's gone. Why? Anti-scald shower valves rapidly adjust when pressure drops on one side, usually cold. They make the hot water pressure drop too, so you don't inadvertently scald yourself. That bad dance is now over. Thank you very much. This is a good thing. But all of those valves have pressure drop in them. The old ones didn't. These do. So I decided to measure it. We set up, using the same equipment, we set up a slightly different experiment. You can see here that we would bring cold water to the cold side, cold water to the hot side, set the valve to the maximum flow rate, and then we would test either the tub filler or the shower. Notice that the pipes are oversized. I want to have the signal to noise ratio be right. The signal is what's going on here in the valve. The noise is what's going on in the plumbing. And we measured the plumbing pressure losses and we subtracted them out from our total numbers. Pretty straightforward, but there's no reason to make it a problem for the measurement. So we made the pipes big. All right, we have data now on half a dozen of those, maybe more. For all I'll go back up. For all of the shower valves that we see on the market, all the trim kits on the box stores from the supply houses, each one of those companies has one, maybe two valves behind the scenes. It's all about the valve from the water's point of view. It's all about the looks from the trim point of view. I don't care so much about the trim. I care about how the water works. Try to think like the water. What's it going to see and feel as it goes through the pipe? Is it easier for me to get to the finish line, or is it a pain in the neck? I want it to be easy, less pressure loss. So we've measured all those sorts of things. And here's what happens at the end. Shannon, we've talked about this before, and you'll get to raise this in just a second, but I like a shower to feel good. To me, that means I have to actually notice that I'm in it. I want it to feel on my back. I want to know what's happening. It has to have a right spread. I'm getting a little slow in my old age, so it has to cover more of my back than it used to. I want to know I'm in a shower, right? Everyone's got a different desire for their shower. Some like it softer, some like it harder, some want to be able to get in and out quickly. Others want to, that's how they wake up in the morning. That's me. I wake up in the morning. It's fine. The problem is that pressure, a hole with pressure behind it is called a fixed orifice. It follows the laws of physics, which says if you rate my flow at 60 PSI, which is what we rate faucets at, and I only have 30 PSI, I'm going to get 0.7 of the rated flow. It's actually half the square root of 2. It's the same formula that's used for blower doors and duct testers. It's exactly the same physics. If you only have half of that again, or a quarter of your rated pressure, you get half of what you started with. No wonder people don't like the way things feel. If they have a fixed orifice faucet aerator and their pressure is between 15 and 30 PSI, they're only getting half to 3/4 of what they thought they bought. No wonder they're not happy. But if you get a faucet aerator that's got a special single core pressure compensator in it, you'll follow the green line. And if you get one with a dual core pressure compensating aerator in it, you'll follow the gold line of performance, which looks to me like you're well over 95% down to 15 PSI. I do not know what my operating pressure is going to be today. None of us do. Unless we live on our own system where we're in control, the municipality changes all the time, every hour of every day. So I don't know what it's going to be, but I can overcome it by putting in the right kind of aerator. And if you look carefully, these are the fixed, the gray line box is the fixed orifice at 2.2, 1.8, and 1.5 gallons per minute. You see the single core orifice where you can see the O-ring. If you look really carefully, you'll see scallops around the O-ring. When the pressure is high, the O-ring compresses, closes the holes. When it's weak, it opens up, keeps the holes wide. And if you look carefully, this one here at 1.2 gallons per minute has 2 O-rings in it. They call that dual core. The company who makes them is called Neoperl, Neoperl. If you contact them and tell you that you heard this talk, they will help you get a sample kit so that you can start playing with this. It turns out there's 3 different flow patterns, spray patterns, stream patterns for faucet aerators. One that looks like champagne bubbles, one that looks like clear column of water, and one that looks like a mini shower head. You can pick at any of these flow rates. And what's really special is they've just announced that all of these flow rate ranges will now be in dual core in retail space. And when you're buying new equipment, you just have to specify you want that aerator. They sell to 90+% of the US market and European market. They're the intel inside, if you will. Let's look at the shower heads. This is the wimpy shower head problem, Shannon. Shower heads are rated at 80 PSI. The plumbing code says you can't have more than 80 PSI anywhere in your building. Your second floor shower will never have 80 PSI, period. End of conversation. Won't happen. So you're already somewhere down the gray line. If you only have 40 PSI, you're going to get, 0.7 of the rated flow. If you're only at 20, you're going to get half the rated flow. If you have a single core pressure compensating aerator, and if you look carefully inside the top of the shower head, you'll see that light blue ring with the black O-ring in the middle. That's pressure compensating. You will now have 85 to 95% for all operating pressures that you're likely to have. You will be happier. Why? Your shower head spray pattern was rated at 80 PSI for comfort. No wonder it feels bad. You're not getting that PSI. The single best thing you can do to fix your existing shower head is to take out whatever's inside there and replace it with one of these pressure compensating devices. And that's available and sellable too, as a little insert that you can buy about 1 inch long, and you can magically make it work for yourself. It's a good thing. But, these are the things we learn over many years of looking. All right. You're all going to ask me about heat pump water heaters today because I keep getting that question a lot. So we'll come to it. It's a great idea. It's still a new water heating technology. I know some of the people on this call have been doing water heating much, much longer than I have. And heat pumps have been around a while, but modern era is less than 15 years now. Okay? They are not simple change outs, even though we're told they're very simple to install. Yes, they are, but they're different. Did you know that water heaters have air filters? Heat pump water heaters have air filters. When's the last time you actually changed your own furnace filter? Go ahead, raise your hands. You're among friends. I hear that admitting this is a first step. And so it's a problem. The plumbers don't know there's filters. The customer doesn't know there's filters. When the filter clogs, they don't know why it didn't work. Who are you going to call it to in the morning? The people who know how to deal with the water, or the people who know how to do with air conditioners? because it's basically it's a heat pump on top of a water heating tank. Come on, that's what we're selling the majority of, these unitary heat pump water heaters. So where does the heat come from? That turns out to be an important question. And how do we manage the exhaust air to prevent condensation on surfaces? These two questions have been bothering me a lot for the last year. And if you look around, I've been putting in a fair amount of public comment on various code proceedings because the physics that we put into the code are about building science, not just because the manufacturer says install my equipment this way. We have to make sure that we don't harm the occupants or the buildings. And I think it's essential to bring water heating into the building science community. Very, very few people who are in water heating manufacturing participate in the same kinds of events that we do on this call. It's not what they do. They make product. Okay? We have to teach them about these things and help them learn how to make it all make sense. So this is the question I asked a year ago. Is conduction alone sufficient to provide the heat for a heat pump water heater? And the answer is no. This is the best case. The unitary heat pump water heaters that are being sold in the US, Canada are based on a method of test at 67.5 degrees, 50% relative humidity. I would call that indoor temperature and humidity conditions some of the year in many places. Fair enough? That's about right. It's 67, 70 degrees. It's close. Imagine the water heater would have to be put on the first floor of a 2-story building with a conditioned basement or crawl space and a conditioned attic or second floor. We don't put water heaters there. We put them in basements if we have them. Why? Because that's where you put water heaters. When they leak, they're already down near the bottom. They can't hurt much more of the house. Well, that means you can't get conduction from the floor. And we're building passive house, right? We insulate the floors, don't we? There's no conduction coming into that room, right? The only place to make the energy balance work, this is the best case, is here in the middle of the building. Conditioned spaces in front are all insulated, roughly all 6 sides. I did this experiment for several different room sizes. I've got testimony that we've submitted to the IECC. You can read all about it. It's there. It's been going on for a little over a year now, so there's lots of places to look. So this is the math showing the heat gain into a room via conduction. I did it for different sizes of space and volume. We all talk about volume, 450, 700 come from the manufacturers. Here's the square footage. If you have a delta T, let's pick the 450 because manufacturers want to go there. I need to maintain a 25-degree delta T across the envelope of that room that I just showed you for every hour I want that heat pump to operate. That means if it's 70 degrees outside, that room is at 45 degrees, if I did my math right. Is that right? 45 degrees is close to the cutout point of the water heater, and it's real cold in that room. I'll come back to the real cold in a little while. It's not going to be happy. The efficiency at 45 degrees is going to be down here. If it's running in heat pump mode, it's iffy. It'll be about a COP of 2, which means I have to run it longer to do the same amount of work because I was hoping for a COP of 3 or more. If the UEF of a piece of equipment is rated at 3.5, the COP has to be higher, like 4. Why? There's standby losses in the UEF. You have to overcome losses. So in order to have high COPs, I need really high temperatures. That's not what we run our houses at. That's called garages in California in the summer or Phoenix in the summer. It's not indoor temperature conditions. Okay? If you have an R10 wall, which is a 2x4 wall that's insulated, there are no numbers that allow you to run 24/7 in heat pump mode. I want heat pump mode. I want it to be efficient. So do we all on this call. We want them to be efficient in operation. All right. We still need unrestricted access to thermal resources. This is another way of looking at the problem. The amazing shrinking room research that NIA sponsored shows pretty clearly that full louvers or grills top and bottom, high up and high down within a foot or so of the ceiling and floor will give you COPs above 3 consistently, almost independent of room size. We need to make sure that there's energy coming in and out of the space where the heat pump is located, or the heat pump has access to energy from in and out from the room where it's located or the rooms next to it. We've worked out the basic math. You need roughly 40 CFM per 100 watts of compressor power. That's the equipment that we're selling now. It seems to have those numbers in it. And from this graph, it looks like 80 square inches per 100 watts of compressor power would be just about right. Cool. Now we have numbers we can build to. We have to avoid condensation on surfaces. These are shared by my friend Ben Knopp, who I've been working with on creating this public testimony. If you see there's a schematic, an outline of a missing air handler. The heat pump water heater was installed perfectly adequately in a very large room. It said it was large enough according to the manufacturers. That's great. The problem is it was blowing its exhaust air below the dew point straight at the metal of the air handler unit. So it rotted it out, completely filled with condensation and mold. They had to remove it. Oops. Closet install. Again, almost a correct install. It needed to be a little further from the wall in this case. It has a fully louvered door, which claims to be it claims to be okay based on the rules, and yet the room rotted out. The cold air coming out of the heat pump was below the dew point. Even though the air coming into the room was plentiful, it was full of moisture. Guess what condensed? The moisture. Where? On the wall. Oops. This wasn't even in the interstitial space. This was directly on the surface behind the water heater. Oops. We have to pay attention to these conditions. So this is looking at the condensation problem of the interstitial space. Very typical conditions. We're creating a cold room. We just talked about it, bringing it down to 45 in order to run it 24/7 for the conditions that I might want to run. I don't know if you're going to need 24 hours a day of hot water, but I want the installation to be safe for any number of hours of operation in heat pump mode. Don't you? So there we go. This shows you the condensation problem in the wall. And this is where the moisture tends to be showing up. It ends up showing up at the bottom of the interstitial spaces. Moisture sits there long enough, you'll end up with moisture damage. If you end up with that long enough, you'll end up with mold and mildew. And now you've harmed the building and the occupants. So let's look into the future. High performance programs. We're all participating in them. We're all trying to do things that help with incentives. I want to pay for long-term persistence. I want to pay more in the 10th year than the first year. Why? Don't you want it to last at least a decade? Don't you want to sustain the energy and carbon benefits for at least a decade? How about 20 years? Pay them twice. Don't pay upfront. Upfront costs always go wrong. Always go wrong. I've been watching our industry since the 1970s. We've got 3 or 4 examples. When you incent first costs, you get high costs. That's what you get. After rebates, you paid for a lot of people to sell and install it, but you didn't get stuff that works. You just got high costs. We've done that more than 3 times in my career. I'd like to prevent this the 4th or 5th time. We want to simplify code compliance. I hate paper code. I don't like calculations to prove I'm efficient. I want to measure what I claimed. For the same amount of money as gaming the system, I could measure what I got at the end of the day and know that it was working as intended. People talk to me all the time about the best thing since sliced bread. Lots of companies come up and say, my widget is better than you've ever seen it before. No one's ever heard that, right? Right, Sean and Zach and Ilka, Shannon. We all hear that. That's our daily lives. People come and sell us a new thing. That's great. I make sandwiches.
Gary, I'm just going to jump in and give you a time warning. It's 1:15, and
Good.
Thank you for making sandwiches.
We're making sandwiches. We have to make good sandwiches. We need feedback. It has to be immediate. It has to be actionable, and multiple people need the results so that they can create the feedback loop. We need replicable business models so we can repeat ourselves into the future. Someday we'll talk about competition in service of conservation. Everybody likes to win an award. Let's start giving out more awards. All right, we're almost wrapped up. I think our technical skills coming to sessions like this are prerequisites. Learning the tasks we have to do on our daily jobs are prerequisites to play in the game. Our communication skills are even more critical. I'm going to share with you 6 or 7 books that have made a huge difference to me. How to Win Friends and Influence People by Dale Carnegie. Most of us think it's what used car salesmen do to sell us a car we don't want at a price we don't want to pay. It's not. Another book that I found very helpful, How I Raised Myself from Failure to Success in Selling by Frank Betcher. Frank Betcher used to play baseball way back when. He hurt himself. He had to go into a new career. He started in insurance. He was failing in insurance, went to listen to Dale Carnegie, give a talk. 11 years later, he retired a millionaire, and this is in the 40s. That's like serious money. This isn't about insurance sales. It's about how to learn to ask the right questions so that we can get better answers from people to help them get what they want. Personality Plus by a woman named Florence Littauer and Personality Profile by Florence Littauer and her daughter are about, what do we call those? Social styles. Everyone has 2. We've all taken Myers-Briggs. If we're old enough and in our careers, we've probably taken a Myers-Briggs test. I'm an ENTJ. That's nice. I don't know what to do with it, okay? But Florence Littauer takes what came from this guy named Hippocrates, the first do no harm guy, Hippocrates. She brings his words into the modern era to teach us how to better understand social styles and what to do with them. People have 2 styles, primary styles and a backup style. Backup style is where they go when they're cornered. You want a good rule? Don't corner people. It's really simple. She tells really good stories. It's hilarious. It's worth reading. You'll remember it. The next one is The Great Connection by Arnie Warren. I learned how to talk to my teenage son from that book. The Go-Getter is about a story by Peter Klein. It's a great short story. Take you less than an hour to read it. And The Richest Man in Babylon was published in the 20s. It's about how to manage your money. Not in the stock market. I'll give you a clue. You should read the book. Now, here's the challenge. It's the same one I gave at ACI in 2012. I want you to read the 3 introductions to How to Win Friends and Influence People. After you've read all 3 introductions, and I know there are 3, you have permission to reach out to me. And if you tell me you've done it, we can then talk about what you learn in those and what happened to me because of it. I wouldn't be here today if it wasn't for reading these books and learning the principles they teach. I have to have technical chops to do my job. But if we can't communicate what we're doing, it doesn't really matter. All right. Thank you. And any questions?
Bravo, Gary. Bravo. Fantastic. I love the reading list.
Do you want me to go back and leave that up so people can copy it?
Sure. That'd be fantastic. So we do have a whole lot of questions, Gary, and we are going to jump right into it. But what's first,
and
Sean?
I can stay 15 minutes after for the normal time, so we're good if we want to keep going.
Yeah, we definitely need to go to the final 15, but first we got to go to sponsors. Zach, over to you.
Yeah, that's right. So I want to give a big thank you to our stakeholder partner, NYSERDA, the New York State Energy Research and Development Authority, and also our founding sponsors, 475 High Performance Building Supply, Ingui Architecture, Partel, Rockwell North America, and Zola Windows. Thanks too to our champion sponsors, Bewizo, Cascadia Windows and Doors, European Architectural Supply, Facro, Icon Windows and Doors, Intelligent Membranes, and Source 2050. And a big thank you to our patron sponsors, Brennan, Holstrom System, Innotech Windows and Doors, Lamolux, RDH Building Science, and Sanderson Sustainable Design. Thank you, sponsors.
Great stuff, and like to see some of those new ones in there too this year to kick off 2025. Great stuff. We've got, let's do a couple questions and then we'll do events. So kicking things off is Chris. Chris, you want to hop on and ask your question to Gary?
Yep. Thanks for the presentation. So I work in California, mostly San Francisco, Northern California, and work on low-income retrofits, decarbonization retrofits. So existing buildings that have a lot of problems, code violations, everything you can imagine, deferred maintenance, mold, everything. one of the projects that we're working on for a demonstration project right now in San Francisco has, it's a 4-unit low-income building, old, 1906 and it's got 5 water heaters that are gas. One is tankless and 4 are tanked. And we're replacing the water heaters with heat pump water heaters and trying to decide between replacing them with 5 or 1 tank, 1 water heater. And we'll have to figure out the billing and stuff. And looking at your presentation, I have to say we are planning to put them outside in a shed, which maybe is a mistake. But
So
anyway,
I have questions for you, Chris.
yeah.
We're probably going to have to do more later, so be sure to reach out.
Okay.
And we can do that. You've got several problems. You have to have enough energy for the heat pump to work right. Otherwise, it's sort of silly. Okay.
Mhm.
If it's outdoors, it needs to be designed for outdoor air temperatures. So in the Bay Area, it's between 50 and 70 most of the year, right? It rarely gets to 80, 85 degrees.
Uh-huh.
It depends where you are, but that's pretty typical. So we have to pay attention to picking a water heater that's designed, the heat pump portion is designed for being outdoors or using outdoor air. That's the most important question. Then you have to decide where you're going to store the water. Maybe we can use the old mech rooms. Maybe we can't. I can't tell that from this call, right? From this presentation.
Yeah.
But you have my contact info. Please reach
Okay.
out and I'll help you figure out where to go next.
Okay. Thank you.
Okay, so we've got about 5 minutes to wrap up the hour. So what we're going to do is we will transition to not just the final 15, but we'll do the final 20. So mainly because there's a lot of questions, we got to get through them quick. We'll do our best, and if not, you've got Gary's contact, and hopefully you will sign up for Friday's event because again, another exciting event happening with the Accelerator team, and it is the month of electrification, and this is what we're keep talking about. And so let's get back to Gary. So Gary, the next up in the queue is Mo. No, sorry, Lauren. Do you want to hop on and quickly ask those 2 questions because we do got a bit of a lineup. So
Sure,
over
I'll
to
be
you.
speedy. Hello, Gary. Thank you for
Perfect.
the presentation. My question is about, so we're speccing a lot of heat pump water heaters in our designs, and we're doing hot water recirc. And I know a lot of the literature coming out from Ream and A.O. Smith is advising against recirc loops, and I think they're talking about continuous. We're doing ours on demand, usually with motion sensors, and I was just hoping you could comment on why the literature is saying that about the continuous, what that's doing to the heat pump. And then if there's anything we should be watching out for when we're doing our on-demand systems with the motion sensors to make sure that they are indeed operating in that heat pump mode that we want them to be functioning at. I have another question about, and I'll just sneak this in, about potentially following up with you to get your letter template that you've used to AHJs to get approval for 1/4-inch twigs. If you don't mind, I'll email you.
Reach out. Yes.
Okay, thank you.
Okay, so to the first set of questions, when you run a recirc loop 24 hours a day, every time you leave the water heater, you start at, let's just say 130 degrees, leaving the water heater, and you come back something cold. It will pick 5 degrees colder, right? You have to reheat that 5 degrees of loss around the loop. Does that all make sense, Lauren? Okay. If you do that 24 hours a day, because that's a control strategy, turn on the pump and never turn it off, you're going to suck heat out of the tank many, many hours of the day when no one's using hot water. And every time it comes back, goes out at 130 and comes back at 125, it starts to leave at 129, then 128, then et cetera, et cetera. At some point, it gets cold enough to tell the heat pump to fire again. Heat pumps are really slow to heat the water. They now have a 50-gallon tank that's 75% not hot. They've got started at 105. They got to warm it back up to 130. That doesn't take minutes. That takes hours. It can't keep up. The heat rate of the heat pump is barely able to keep up with the losses of the loop. And so it's not running because it wasn't triggered. So it's not keeping up. It's getting cold. And so anything that sucks the heat out of the tank and that's not a use is really hard for the users because they wanted the use, not the loop. They wanted the loop because the architecture is spread apart, right? It's solving a set of problems. So on demand minimizes how much energy comes out of the tank by a lot. We could do another session for this group on recirc loop control strategies, but fundamentally that's the problem. And that's why we want to have on demand. Next question.
Mo's gonna jump off. So Mo's question is, can you please sorry, I had it and I lost it. Can you please speak to the run and rise ratio optimum?
Run and rise of what? Oh, the distance? What do we think run and rise means? Mo, if you're here.
Mo
Run and
had to
rise
jump, but
ratio.
she asked that question when you were talking about plumbing up versus plumbing down.
Okay. So the plumbing up is, look, if you put plumbing between floors, you're feeding the second floor, you put the plumbing in the ceiling of the first between the floor of the second, you have 5 feet up to the furthest fixture, 4 to 5 feet. It's within a cup. If you're doing between the first and second floors and you have to feed the first floor, which is a slab on grade, then you have to come down almost 10 feet to get to the furthest fixture from the ceiling, which is the angle stop for sinks. You need some wiggle room. So it's about twice the distance to plumb down as it is to plumb up. Sometimes you don't have a choice. You just have to do it. If you really want to do better, you bring your loop down the wall. But the basics are practical plumbing. Put the big pipe between the floors where it's easy to work. Put the skinny pipe down the walls where it isn't as easy to work, and it's skinnier. It's easier to run it.
Gary, that hot tip right there with the design of putting that tank in the main floor, man, I'm telling every designer. I'm not like, honestly, Zach, you might have to pump out this recording faster so I can watch it again this weekend. Because there's some hot things that I'm clipping and being like, you designer, you need this one. Plumbing guy, you need this one. Someone else, you're gonna need this one. So many great
Well, and
slides.
can
here,
we
Gary.
just continue this for another hour and a half? And Gary, can you build a
Yes.
presentation on those research strategies? Because I need this.
So,
I've
Yeah.
got the research strategy presentation already built.
of course you do.
Great.
All right, Kevin, over to you.
Thanks, Gary. So my question really is, are the rules of thumb of hot water heating? I've heard you speak of them in the past, but I thought it'd be great to share with the group. I think I've heard you say large branches and small trunks, and now I have twigs into my my vocabulary now. And then also, if you can expand on the principle of hot water piping, meaning like the insulation. I've heard rules of thumb of like 2 times the diameter of the pipe is the optimum insulation for that, but I also think that depends on the insulation type. So if you can just expand on those 2 topics.
All right, Kevin, you're going to have to remind me of the first one, but I'll answer on the second one first. So I was introduced to the German energy code 20-something years ago by people who sell electric heat trace. And they said, you really need to look at what the German energy code says you have to do. And the German energy code says for all pipe 1 to 4 inches in diameter, they say it in millimeters, but 1 to 4 inches diameter, the wall thickness of the pipe insulation shall be equal to the nominal diameter of the pipe. And I asked why. And they said, well, we like it because it means you have equal heat loss per foot. And because we sell electric heat trace, we get to sell 1 controller for all diameters of pipe that are insulated that way, because all of it will heat and cool at the same rate. And so that seemed to be a really, really elegant solution. So we adopted that principle for the United States, and we proposed the same rule for all pipe up to 2 inches in diameter. The reason we went to up to 2 inches is that Gary's best guess is that somewhere over 80% of all pipe ever installed in the United States and Canada is 2 inches or less. So let's have an 80-20 rule. It's applicable for all that. When I have 3-4 inch pipe, I expect an engineer to show up, but not that they're any better at the math than anybody else is, but I'm expecting them to be on the job so they get to pick other numbers. And so the wall thickness equal to the nominal diameter is my current favorite because it gives you almost exactly the same heat loss per foot of pipe insulated that way. You want better R value or K value, use better pipe insulation. You'll have less heat loss, but you keep them all the same. They'll all act similarly. So that's the second question. What was the first one?
I think it was the general rule of thumb of big branches and small trunks.
I like trunks and twigs. I don't like branches. Sort of the plumbing code calls things fixture branches, branches. They have this thing called risers. And they have mains, they have trunks. I was in the state of Wisconsin once for a week. I was in 3 different cities. They got 3 different definitions for the pipe that serves a single fixture, hot and cold water. I decided I was going to stick with twigs because everybody knows what a twig is. And it's clear which one I mean. Okay. Ben Knopp, who I see on the call, and I have been working on a plumbing design strategy where we had a spine of plumbing running down the basement with ribs going up to become risers to go all to the apartments on the other floors. Everybody see the image? So we went to a different analogy for that portion of the system so we could be a little more clear where we meant. Once we get at the apartments, we call them trunks, branches, and twigs. I like trunks and twigs. Branches sort of by definition are fat, relatively speaking, and they don't need to be. Next question.
Then I think I heard you say 1/4-inch pipes, and then you need a letter to get the 1/4-inch pipes in from code officials. What's your sweet spot for? Is it 3/8 or is it 1/2 inch? What's your twig size normally? Depends.
Up until fairly well, yeah. Your authority having jurisdiction gets to decide. Okay. But the plumbing codes in most of the US and Canada assume a minimum diameter of 1/2 inch. It says so in chapter 6 or their design or appendix. The international plumbing code says for certain fixtures you can and appliances you can use 3/8 tubing. Okay. They allow 3/8 tubing for filling toilets. Toilets fill at 3 gallons a minute. In PEX, that's 10 feet per second, which the plumbing code thinks is a little fast. I don't want any velocity noise either, but the real problem with 3/8 tubing and 3 gallons a minute is the pressure loss. And on a 3-story apartment building, you can't afford the pressure loss to that toilet under normal operating conditions, so I use 1/2 inch. It's a bucket, let it fill. There's no reason to slow down its fill rate. I don't want any noise. So I adjust the diameters based on the science, not what the code says. Anything less than what's allowed by the code in its documents requires a letter asking for alternate methods and means. And that letter allows you to make a justification for using skinnier tubing. Larry Weingarten, who I think was on the call, I saw him earlier, asked for that letter of permission in California when he built the house he lives in now for 3/8 tubing, and more recently for a home that won a design award at the Tiny Home Awards that were in Orange County, California last year. It has now been situated in Salinas, California with 1/4-inch tubing, and that is the letter you're all asking about. It had to do with what's the pressure loss per foot of pipe, how many feet of pipe, what's my starting pressure, what's my residual pressure, is the residual pressure above what the code minimum allows. That's how you do the math. That's how we got the letter approved. Can't guarantee it'll happen in all cases, but that's what was done.
Fantastic.
Ilka, over to you.
Yeah, awesome. Thank you so much for such a great presentation. I think we basically answered my question because I wanted to know a little bit more about the circulation loop controls, and we just established that you're going to have to come back and have a whole presentation about it because there's so much to talk about. I did want to say real quickly, I think what struck me the most about your presentation is just realizing how important is where you place your hot water heat pump in relationship to other systems, just relationship to the wall, relationship to the air handler. I mean, it's totally makes sense, but to be honest, I never really thought about it. And now you definitely have me thinking about all the mechanical rooms that I have designed or built. So hopefully it all goes well there.
So Ilka, there are 6 control strategies for recirc loops. You get to think about what those might be before we talk next time. There are not 7, there are 6. We've been studying this for a really long time. If we find a seventh, I'd like to know about it. They're not there. But the question is, how do they compare to 24/7, which is the single most energy intensive? I saw a question in there about gravity loops. That's one of the 6 types, but it's a gravity loop is a 24/7 without a pump. And they lose heat without a pump, and they have high delta T's because they need them in order for the gravity loop to work. And so everything seems to be roughly proportional to 1 gallon a minute and 5 degrees delta T around the loop. If you increase the delta T, you've lowered the flow rate. If you increase the flow rate, you lower the delta T, you get to pick, but it's always roughly proportional to this 1 gallon per minute and 5 degrees delta T. Doesn't matter how big the loop is, that's what the math looks like. All right, so to the other piece of the puzzle about where you put things, if you have a mechanical room, anybody on the call have basements? Good. Your heating system is in your basement, yes? The air handler is in the basement. Air-to-air heat exchange is in the basement. Best solution we've seen so far. Bring in fresh air from outside, collecting bad air from bathrooms and other key places. Bring it into the basement. Let it fall on the floor in the basement because you have a return in the basement for your heating and air system. If it doesn't fall on the floor, connect it into the return directly. Okay? Don't need separate ductwork. You need really good heating and air ductwork. Really good. Why? You want the right registers in the right places. You want lots of flow, etc. And because we can get them, maybe we should buy heating and air equipment with really low watts on the low fan speed, so that we're moving air around the building to circulate it. Right next to all of that is your heat pump water heater designed to use indoor air. Hold on a second, my dog's having heartburn. I'll be right back.
Sure, Gary. And I was just going to put into the chat while Gary's taking a break that if we don't get to your question today, it's not because we don't love you, and we can connect you with Gary to answer your questions after today, but we just might be running out of time. So hopefully we'll get to all the questions, but if we don't, please understand and let us know. If you need those burning questions answered, we'll connect you with Gary. And
Yeah,
Gary, I think you answered Reed's question already about the gravity loop.
Yeah, I did, but I want to finish the one I was just on.
You bet.
The last piece of the puzzle is, what do you do with the cold air that comes out of your air source heat pump water heater that was designed for indoor applications, the vast majority of what's been sold? How about we connect the exhaust air of that into the air handler and let the air handler be bringing in all the return air is warmer than the discharge temperature of the heat pump water heater is. The moment you warm the air back up, it becomes less unsafe. It can't condense on surfaces and it can't cause their temperatures to go below the dew point so moisture can condense. The key is to manage and avoid condensation on surfaces. The only way to do that is to raise the temperature of the exhaust air quickly to bring it above the dew point. The best solution we've seen is to co-locate and connect the exhaust of the heat pump water heater into the air handling system of the building and let that bring the temperature of everything up and distribute the cold air diluted throughout the rest of the building. That answer came to me from talking with a good friend named Gary Nelson, effectively the inventor of the blower door and duct tester that we all know and love today. We were at a conference a year ago. I got the answer, and that made the most sense to me of anything I've heard in the last year. It's worth doing. If you can do it, co-locate them, it manages the air. Next questions.
Perfect. Our next question comes from Taylo. Taylo, would you like to come on and ask your question? Let me know if you need a reminder.
Yes, the question was really, where would I find equal knowledge in the East Coast or New York City? Somebody I could hire to do the system.
Well, we do consulting all over the country.
Oh, thank you. Okay.
So you can reach out. I'm already working with folks in New York City.
Absolutely fantastic.
Perfect. Thank you, Taylor. It looks like you just found your next customer, Gary. Reed, let me know if Gary answered your question already. Actually, it looks like Reed took off. So up next is Gail. Gail, are you still with us? Looks like you are.
Yes, I am.
Hi.
Can you hear me? I wasn't prepared. I thought you were going to read the question.
I can if you'd like me to, Gail.
Sure.
Gail asks, is there any good data on the lifespan of electric heat pump water heaters? I've heard it is quite short.
They're an evolving technology, Gail.
All right, well, you know, we have a lot of questions today, so unless you want to elaborate, Gary, don't feel like you have to.
It's a new technology. You should plan on making it easily replaceable. Do not hard pipe anything in. Make it easy with a couple of valves to remove things if you have to in minutes, not hours. That's my current best advice.
My plumber said maybe only 4 years. Is that?
It's certainly possible, but that has to do with it's probably the heat pump they're expecting to fail, not the water heating side of it, which is electrical and refrigeration questions, not water heating questions. But they're warranted for 10 years. It's just hard to go in and pull something out of a basement that's 3 stories down and bring it back up again.
Right.
And the cost of the equipment's paid for, but not the installation replacement. So it's a problem.
Okay. Thank you, Gary.
I don't have better answers at the moment.
No, but that's helpful. Thank you.
You're welcome.
No worries, Gary. And you know what? We have just crossed the threshold of 1/4 past. So I want to thank Mags and Prescott and Bruce, myself. If you really need your burning questions answered, please reach out to us below at passivehouseaccelerator.com or by the information Gary shared.
Can I ask
Kevin, it's all you.
one last question? Is there any saving grace hope manufacturers out there for solar thermal? Any manufacturers currently that are selling complete systems that you know of?
I do not off the top of my head, but I'm pretty sure that Larry Weingarten, who I think is still on the call, will have an answer to that, and he'll reach out to me and we'll reach out to you.
Awesome. Thank you.
Thanks, Kevin. Thank you, Gary. Thanks, Ilka and Sean and Zach and Kim, who had to jump early, and to all of you for joining us today. Spectacular presentation. Look for it online in the coming days. And any final words, guys, before we sign off?
We love Gary.
We love Gary.
Yes, we
Thank
do.
you, sir.
Thank you
Thank
very
you.
much for the
See you
opportunity.
Friday, Gary.
Have a
All
great
good.
day, everyone.